Hello and welcome to our 16th session. Wow, we're getting up there. And today's session we're going to look at the metal semiconductor or Schottky barrier junction under external bias. And as soon as I say external bias, we should immediately be thinking of non-equilibrium. So the Fermi level is not going to be straight and horizontal throughout the entire structure. And this material is found in Chapter 9. And before we get started, I would like to share with you a marvelous aria from Giuseppe Verdi's La Traviata with Teresa Stratus as Violetta and Placido Domingo as Alfredo. Marvelous line that I particularly love. Io vivo quasi in cielo, I live as if in heaven. So enjoy, and we'll see you back in a little over 4 minutes.
Lunge da lei, per me non va diretto. Volaron già 3 lune da che la mia violenta agi per me lasciò dovizie, onori e le pompose feste. O voglio magia pezza, vede a schiavo ciascun di sua bellezza. Ed or contenta in questi ameni luoghi che tutto scorda per me. Qui presso a lei rinascer mi sento e dal soffio d'amor rigenerato scordo le gaudi suoi tutto il passato. Dei miei bollenti spiriti il giovanile ardore e la temprata e placido sorriso dell'amor, dal di che disse vivere io voglio te vedere. L'universo è in me io vivo quasi in cielo, dal di che disse vivere io voglio te vederla. Sì. L'universo è in me io vivo quasi in cielo, io vivo in cielo dell'universo immemore. Io vivo quasi in cielo, sì, io vivo quasi in cielo, io vivo quasi
This is an outline of some of the topics we'll be covering in session 16. We're going to start off with a little bit of a clarification of what we mean by depletion capacitance, and then we'll summarize the Schottky barrier structures. And when we're talking about Schottky barriers, we'll really be emphasizing the rectifying structures. And specifically, we'll be talking first about N-type silicon under an external bias, and that's going to be the bulk of our discussions. We'll just sort of mention the p-type because everything is the opposite, but we won't go into too much detail on the p-type. We'll be summarizing the non-equilibrium currents for n-type silicon. Again, our concentration is going to be on n-type silicon. And the reason we do n-type silicon is Schottky barriers basically are used, at least for modern semiconductor devices, much more with n-type than with p-type. And we'll be looking at some examples of Schottky barriers on things called MESFETs and SITs in our final sessions. And then we'll be looking at, we won't derive, the derivation is in the text, but we'll at least be looking at the mathematical expression for current in n-type silicon. And then we'll talk about, again, the depletion with W. We mentioned it in our last session. We'll go into it in somewhat more detail. And the electric field in a Schottky barrier. Again, these are all rectifying Schottky barriers. When I say rectifying, I mean they contain a depletion region, and that's the characteristic for a Schottky barrier junction rather than a non-rectifying, which we mentioned last time, and we won't go into too much detail again on that. And then finally, we'll be looking at, hopefully if we get to it, the depletion region capacitance in much more detail and the effect of the doping density. And that should wrap it up. All right, let's get started with a short note on depletion capacitance. Now, this is the basic relationship for a capacitor. Charge equals capacitance times voltage. And this is only quote-unquote good if the capacitance is constant. And then we have a linear relationship. The higher the voltage, the more the charge. However, if the capacitance is not constant, in fact, in the depletion region, the capacitance is not constant, it depends on the voltage, and that's something that we're going to see in some detail. We apply a voltage, and the capacitance changes. It either gets bigger, in the case of forward bias, or it gets smaller in the case of reverse bias. Why does it get smaller in the case of reverse bias, which is a very important case? Because the depletion region widens, and the wider the depletion region, the smaller the capacitance. So if the capacitance is a function of the applied voltage, then we can't use this equation anymore. We have to use a more general equation. And what we do here is we say, okay, we're going to wiggle the voltage, we're going to apply a little bit of voltage, and we'll see how much charge is either taken away or added in that particular region, and that we're going to call the capacitance. Then we go to a different region with a much different voltage, and the capacitance will be different. Clearly, if this thing doesn't change, if this is constant, then the relationship is linear, and C equals dq dV collapses to the more familiar equation. C is equal to Q over V. So that's just something to keep in mind, and a little bit of a clarification over what we had in the last session. And we'll be going back to this when we talk about the depletion capacitance in much more detail. Okay, next topic is a summary of Schottky barrier conditions. And let's just kind of review these from our last session and from Chapter 8. For n-type silicon, the work function of the metal is greater than the work function of the silicon. Therefore, the Fermi level in the silicon is higher than in the metal. So when we bring the two materials together, the metal and the silicon, electrons flow from the silicon into the metal, and that's what forms the depletion region, because the surface area or the surface region at or close to the junction becomes depleted of electrons, leaving behind the ionized donor atoms, which are now positive because they've given up electrons, and therefore we have a charged depletion region. For p-type silicon, exactly the opposite. The work function of the silicon is greater than the work function of the metal, so that the silicon has a lower Fermi level, and electrons flow from the metal into the silicon, and that leaves the silicon depleted of holes because it's p-type, which uncovers their ionized ions or ionized atoms, which are acceptor atoms, either arsenic or boron, and they are negatively charged. They're negatively charged because they've accepted electrons from the valence band. Okay, so this region, point 3, is simply a restatement of that. The region adjacent to the interface, by the interface, the metallurgical junction, the point where the metal and the silicon come together, is depleted of mobile charge. A barrier is formed at the junction which inhibits charge flow. So there is a potential barrier which is formed at the junction, and this barrier inhibits further charge flow. And exactly when this inhibition of charge flow is such that the Fermi levels in the metal and Fermi level in the silicon become congruent, and that's when charge flow stops and we have equilibrium. And we'll just mention again for non-rectifying junctions, in the N-type, it's the same condition as for rectifying junctions. In the P-type, and electrons pile up at the interface. So the interface, rather than becoming depleted of charge, actually becomes charge rich, if you will. And P-type, again, you can see the exact opposite. So there's 4 cases, but these 2 cases are not terribly important. But for the non-rectifying junction, we can say that no depletion region is formed, and current can easily flow in either direction. Okay, so now let's take a look at the N-type silicon. That's going to be the bulk of our discussions under external bias. So we have an equilibrium situation in which the Fermi levels are congruent. There is one Fermi level for the entire structure, and by convention we agree, we don't have to, but for our discussions we're going to agree to ground the silicon and apply our bias to the metal side. Thus, as we change the bias, or change the voltage, same thing, the metal energy levels will slide up and down with respect to the silicon, and the silicon will remain at 0 potential. And this is important, number 2. All the voltage must appear across the silicon, where it appears upon the silicon. Where it appears on the silicon, we'll see in just a second, but the metal is a field-free region, and it does not support energy or voltage differences. Positive voltages are always associated with lower energy levels, again because we're talking about the energy band diagram, which always references energy to electron energy. Higher electron energy, we go up, and that is for electrons. Exactly the opposite for holes. For holes, higher electron or higher energy, we go down. And the reason is that, or the analogy I should say, is that holes are like beer bubbles or soda bubbles. They tend to float up, and if we want to increase their energy, we have to push them down. So as the voltage goes up, the energy goes down. And as with all circuit elements within the silicon structure, we ask, where does the voltage drop? Well, the voltage is always going to drop across the higher resistance area. And where's the higher resistance area? It is precisely in the depletion region. So we're going to find that all of the voltage is dropped across the depletion region, and that is a big deal. When I say all the voltage, I mean VA. A is for applied, and V is voltage. Okay. Voltage drops are always associated with changes in energy. Drops and changes are the same thing, which are in turn are associated with band bending. So all these things are really one and the same. Whenever we have a voltage drop, we have a change in energy, and that change in energy produces a bending in the bands. Which bands? E0, EC, EI, and EV. And for N-type silicon, we'll be mostly concerned with EC and EV. Okay, so let's start with N-type silicon and a positive bias. So this is what our structure looks like. VA is now positive. There is no drop across the metal because it's a perfect conductor. There is almost no drop across the silicon. What there is of it, we simply neglect. And all of the drop is across the depletion region because it has the higher resistance. Okay, let's see. That's basically is what we said before. By convention, we get to slide, we ground the silicon, and we apply our bias to the metal. And this is the energy band diagram for N-type silicon with an applied bias. Now I probably should have put this first. This is the Schottky barrier with no applied bias. And the important things that we'll notice here are the silicon work function, the metal work function, which is higher in N-type silicon rectifying Schottky barriers. The two barriers formed here, the phi I, which is a function of the difference between the metal and the work function, and the phi n, which is a material parameter, and it's equal to the difference between the metal work function and the affinity. Okay, so now we can go back here, and we can see that what happens when we apply a positive bias, the metal work function has actually gotten smaller. So phi sub m minus phi sub s is now smaller. Well, the barrier, phi I, this variable barrier, is a function. In fact, not only is a function, it is equal to precisely phi sub m minus phi sub s. So if phi sub m minus phi sub s in magnitude gets smaller, the barrier gets smaller. Although phi sub bn, this constant barrier, has not changed at all. So this is the energy band diagram for a rectifying Schottky barrier with applied positive voltage N-type silicon. How do I know it's N-type silicon? Because the bands bend up, and that's always true for N-type silicon. The bands always bend up, except I should say the one pathological case in where we're talking about a non-rectifying N-type Schottky structure. So this is just a restatement that the phi n barrier is equal to phi sub m equilibrium without any applied bias minus xi, and that's true for biased or for unbiased. Okay, so this is just a restatement of what we were saying qualitatively. Phi sub m plus V sub A, the applied bias, is equal to phi sub m equilibrium. Phi sub m plus V sub A is equal to the original work function of the metal. Now we know that the difference between phi sub m and phi sub s is precisely equal to the barrier phi bi, so we simply substitute in wherever we have v sub m, we substitute v sub m equilibrium minus v sub a, and what we find is that the v sub a has caused phi sub bi to go down. The barrier goes down. As v sub a goes up, this number here becomes smaller. This is constant, and we're subtracting something that goes up and up and up. Therefore, this goes down and down and down. Okay, so now let's take a look at the Schottky barrier, rectifying Schottky barrier, where I apply a negative external bias. So we go back here. Where is it? We go back here. Instead of being positive now, the V sub A is negative. So if it's negative, this is what we have. And in this particular case, again, I say electron energy increases because it's the energy band diagram. So we find that the work function now has become, metal work function has become larger. It's become larger by the applied bias. So before it was larger than phi sub m was larger than phi sub s. Now it's even larger yet. It's larger by v sub a, so therefore the barrier has actually grown. In the positive, I shouldn't say forward, in the positive bias case, the barrier shrinks, and in the negative bias case, the barrier has grown. So now it's really hard for electrons to go from this point to this point. They see a huge barrier, and that's why this is called reverse bias. I think you can perhaps get the feeling that this is going to be a case where we have low currents, and this is going to be a case where we can support higher currents because the barrier has basically, well, it's gotten much, much smaller. Now let's think about the rather extreme case where I keep applying V sub A such that the metal work function becomes equal to the silicon work function. This thing moves up and up and up a little bit more, so these become equal. The barrier completely goes away. Well, now I have no drop across the barrier because there is no barrier. I have no drop across the metal because metals do not support drops. So where's the drop? I've got applied voltage. Well, the drop must be across the quote-unquote quasi-neutral silicon. It must be across the interior, which means that all of these levels here, E0, EC, and the intrinsic, which I didn't draw, which is down here, they all must tilt up. So, in fact, even when I do have a positive, or have a barrier, there's going to be a little bit of a tilt to E sub C because I do have material non-equilibrium, which means that if I have an electron, say, sitting at this point, well, if it's completely horizontal, it's not going to feel any push to the left. We want it to be pushed to the left, from right to left. Well, if this thing is horizontal, there's nothing to push it. So there really is, and I should have emphasized that in the previous case when we were talking about, there's a little bit of a slant to this. And in fact, when the extreme case never happens in practice, but if we can envision a case in which the metal work function is equal to silicon work function, then this tilt would be much greater and all of our drop would be across the silicon interior. Okay, now let's just very briefly talk about p-type silicon. And we're not going to go into nearly as much detail here, but this is the energy band diagram for p-type silicon under equilibrium conditions. And notice, of course, that the bands bend down. There is a barrier here, and there's a barrier here. The metal work function is less than the silicon work function, so that we have a depletion region formed where the band bending right here of width W. W is the distance from this point, which is the metallurgical junction, to this point, which is the interface between the depletion region and the quasi-neutral or bulk regions. And when we apply a bias here of V sub A, we have the metal work function moving up, or the metal Fermi level moves up, the barrier decreases, and holes move from the p-silicon, in which there are lots of holes, into the metal, and that motion is much easier because the barrier has been reduced. And as you might expect, for reverse bias, we have exactly the opposite. For forward bias, the metal Fermi level moves up. For reverse bias, the metal Fermi level moves down by V sub A. The barrier or hole motion now has increased, and it makes it more difficult to get a current. And exactly the same thing conceptually happens in p-type silicon as in n-type silicon, but electrons turn into holes, and that's enough said on that. Okay, so this is a little discussion. Well, we didn't talk about the Bourdin theory. You can read about it in, I believe it's in chapter 8, and we talk about Fermi level pinning, and we won't say too much, we won't say anything on that here, but if you're interested, you can read about that in chapter 8. Okay, for summary, again, let's go back to the n-type silicon, because that is the more important case. For n-type silicon, for non-equilibrium, again, I mean by non-equilibrium that there is an applied bias and there are currents. For forward bias, I put a positive voltage on the metal, and electrons are now attracted from ground to the positive bias. Opposites attract, so if I have a positive voltage on the metal, it will attract electrons from the silicon. Electrons move from right to left. Electrons, and I emphasize the word electron motion, from right to left is same as hole motion from left to right. Left to right is positive, going in the left to right direction is in the positive direction, so this is a positive current. Electrons moving from right to left is a positive current. And again, just a restatement, the barrier has been reduced and we get a large current, and that current is called the forward current. Under reverse bias, now I put a negative bias on the metal, and electrons are repulsed from the metal into the silicon. They move from left to right. They move in the positive direction. Electrons moving in the positive direction is the same as a negative current. Now here, the barrier, which we discussed not too much, but we discussed, I hope, enough in the text. The barrier is not phi bi, but phi bn, this constant barrier, which is about anywhere from about 0.65 to about 0.8 or so eV. It's reasonably large, and it makes it more difficult for electrons to flow. It is not variable, so no matter what happens with the voltage, the current is pretty much constant. It's small but constant. And I would emphasize that in reverse bias, we still have a current. The current is the reverse current. And because we have a current, we are in non-equilibrium. And this is summarized in this picture here. For a positive bias on the metal, we have a forward current which increases exponentially. We'll see that in a minute. For reverse bias, we have pretty much a constant current. This is almost minuscule change here. The current is constant because the barrier is constant, VBN. That's this. Where is it? That's that must be here someplace. Here it is. Or actually, no, that's for P-type. Sorry, it's this guy right. It must be here. Where is it? Where is it? Here it is, right there. And this is a constant, and this doesn't depend on the bias at all. Therefore, the current is pretty much constant here. Reverse current, small but constant. So this is non-equilibrium. This is non-equilibrium. Where is equilibrium? Right there. Where we have no bias at all. Just sitting there with no bias at all. And everything is quiescent. Okay. That's your laptop when you turn off the power. Right there. Okay. When you turn on the power, you get lots of forward current. You get lots of reverse current all over the place. That's all non-equilibrium. Okay, so now let's look at the expression for the mathematical expression, the quantitative expression for current in N-type silicon in a Schottky barrier structure. This is the result. This is derived in section 9.8. It's derived by a fair amount of detail, so I think you'll get a feel for it if you want to get the complete derivation up there. What we do basically is we say, how much energy does it take to overcome these barriers? How much energy do I need to go from here to here? And it is kinetic energy, it is thermal energy, and carrying through that derivation, we get this expression here. And we see that is heavily dependent on the temperature, both in the coefficient and in the power terms and the exponentials. There are two exponentials, one for forward current, that's this guy here, and the other for reverse current, and this fellow right here. So if we look at the forward current, this is going to be very small. It's going to be constant and small, and it's basically out of the picture. It's equal to essentially 1. But the current is heavily dependent upon the applied voltage VA, and it is exponential. And that's exactly what we're saying here. An exponential increase in current as a function of VA. For the reverse current, VA is negative, and therefore this term is e to the essentially a large negative number, which is 1. So therefore this term goes out, and I get that the current is equal to this term only, and it is constant, and it is very small. And that's exactly what we're showing here. Constant and small for reverse current, exponentially increasing and large for forward current. Okay, so let's take a look a little bit in more detail in the depletion with W. And we found last time that the depletion with W is equal to this expression. We took a look at the different parameters without the VA. There was no VA. And that makes sense because there's band bending. Now notice I'm using VBI rather than PBI, so the units turn out okay, which is good. This is the total charge in coulombs, and this is the permittivity in the silicon. So if you compare this equation with the same equation, chapter 8, which does not include the VA, we see now that the width, the depletion width, changes. It is a function of VA. Now, the question that we ask is a pretty obvious question, is what's this deal with the plus and minus? Well, first let's take a look at the minus sign, the one on the bottom. Okay, so we have a minus sign and we have a VA. Now we're going to assume that VA is positive. VA positive means that we have a forward bias. We're putting a positive voltage on the metal. So what we have here is that VBI, the band bending in the silicon, minus VA. So it's pretty clear that the numerator is getting smaller. And it's getting smaller like the square root of VBI minus VA. So what that tells us is that for a positive bias, forward current, that the W, the depletion region, shrinks. Now we ask the question, pretty obvious, what happens if VA or VBI minus VA goes to 0? If the applied bias is such that this term in parentheses goes to 0, at least in theory, the depletion region should go away. That's the case when the work function in the metal is equal to the work function in the silicon, and there is no depletion region. Never get there, but we can get reasonably close. Well, okay, we just increase V sub A even more, and then this thing becomes negative. So we have the square root of a negative sign. That is not realizable. So we have to realize physically that VA can never be greater than VBI. Traditionally, VBI is on the order of 0.6, 0.7 volts, and a forward bias of anywhere in the range of 0.4, 0.5 volts is considered, well, let's call it fully open. And there is very little depletion region, and we get a large forward current. Okay, so now if we look at the plus sign, V sub A is negative, then I use the plus sign, and they add. So if I have a minus voltage on the metal, a minus bias on the metal, then VBI adds to VA, and this term increases. That is the reverse bias case. So in reverse bias, reverse current, small current, that's this guy over here, reverse current, this term grows and the depletion region gets bigger. It not only gets larger in magnitude as far as the band bending goes up in reverse bias, but the depletion region, the distance from the metallurgical junction to the interface between the depletion region and the bulk, also increases. So the W, which is this distance here, gets larger for reverse bias. And that is shown here in this equation. And we mentioned the last session that permittivity has an effect also for low permittivity materials. Then we'll have this number will be relatively small. This is the permittivity in the silicon, which is equal to the relative permittivity, which is just a real number multiplied by the epsilon 0, which I believe is 8.85 times 10 to the minus, is it 12 or 14, depending on whether you're CGS or MKS. But the important number here is the relative permittivity. For small relative permittivities, this number is small, and W is small. What that means physically is that it's easy to bend the bands. For high permittivity materials, like metal, that would be the highest permittivity imaginable. There is no band bending possible. It is almost impossible to bend the bands, and that is shown in this figure here. Low permittivity band bending easy, high permittivity band bending is more difficult. So if you look at the electric field in the Schottky barrier junction, again, rectifying Schottky barrier junction, the relevant equations, this is the definition of electric field as respect to voltage. We measure electric field in volts per meter or volts per centimeter. This is our basic tool, Poisson's equation, which we derived graphically a couple of sessions back. And the idea here is that there is an electric field which always goes into the band bending. Whenever we have band bending, we have an electric field. When we have no band bending in this entire region here, we have no electric field. And if we have forward bias, this probably would not be completely horizontal. We would have to have a little bit of bending. It would be straight but not horizontal. The field is maximum at the metal silicon interface, also known as the metallurgical junction, and we see that right here because the slope, dE dx, is maximum right there. In fact, in this case, it looks like it's almost infinite, but it's certainly the largest value at the metallurgical junction. And if we look at a schematic diagram or cartoon, this is N-type silicon. We have the quasi-neutral region and the depletion region. And this, as I think I pointed out in the text, is not quite accurate because I must have equal number of electrons at the metal surface and positive charge in the depletion region. Every single positive charge has a line emanating from it which ends on a negative charge. Now, if you have lightly doped material, the positive charge, and again, these are the ionized phosphorus atoms, which are uncovered because electrons, in going to equilibrium, have transferred from the silicon into the metal. If you have it lightly doped, this would be spread out, so the electric field would tend to be smaller and exist over a wider region. And if I have a highly doped material, all the positive ions would tend to be very close to the interface, and that is indicated by this figure here. For lightly doped, large W's and smaller maximum electric fields. Again, the electric field exists at the interface. This point here, x equals 0, is right here. And for lightly doped materials, we have a large W, and for heavily doped materials, we have a small w. And that, of course, that's shown explicitly here. For n large, w is small. For n small, lightly doped, w is large. So all of that makes sense. And the last topic, which we'll just touch upon because I think it's getting a little bit late, and we'll start basically go over this next time. But the next topic is the depletion region capacitance. We want to discuss what happens in the depletion region using right here. We're going to get an expression for the capacitance as a function of the applied voltage, the permittivity, and the doping. And that we will jump into 2 feet first, or head first, whatever the case may be, next time, and we will talk about the capacitance voltage diagram. So we'll start here next time, and we'll end with, I think, something you'll find quite interesting and very nice. Benjamin Zander is a distinguished conductor and a very wise man. So let's listen to some wisdom from Benjamin Zander, and we'll see you next time.
What happened to me, I was in Ireland during the Troubles 10 years ago, and I was working with some Catholic and Protestant kids on conflict resolution, and I did this with them. Risky thing to do because they were street kids. And one of them came to me the next morning, and he said, you know, I've never listened to classical music in my life, but when you played that shopping piece, he said, my brother was shot last year, and I didn't cry for him. But last night, when you played that piece, he was the one I was thinking about. And I felt the tears streaming down my face, and you know, it felt really good to cry for my brother. So I made up my mind at that moment that classical music is for everybody. Everybody. Now, how would you walk? Because you know my profession, the music profession, doesn't see it that way. They say 3% of the population likes classical music. If only we could move it to 4%, our problems would be over. I say, how would you walk? How would you talk? How would you be if you thought 3% of the population likes classical music? If only we could move it to 4%. How would you walk? How would you talk? How would you be if you thought everybody loves classical music? They just haven't found out about it yet. See, these are totally different worlds. Now, I had an amazing experience. I was 45 years old. I'd been conducting for 20 years, and I suddenly had a realization. The conductor of an orchestra doesn't make a sound. My picture appears on the front of the CD. But the conductor doesn't make a sound. He depends for his power on his ability to make other people powerful. And that changed everything for me. It was totally life-changing. People in my orchestra came up to me and said, Ben, what happened? That's what happened. I realized my job was to awaken possibility in other people. And of course, I wanted to know whether I was doing that. And you know how you find out? You look at their eyes. If their eyes are shining, you know you're doing it. You could light up a village with this guy's eyes. Right, so if the eyes are shining, you know you're doing it. If the eyes are not shining, you get to ask a question. And this is the question. Who am I being that my player's eyes are not shining? We can do that with our children too. Who am I being that my children's eyes are not shining? That's a totally different world. Now, we're all about to end this magical on the mountain week, and we're going back into the world. And I say it's appropriate for us to ask the question, who are we being as we go back out into the world? And you know, I have a definition of success. For me, it's very simple. It's not about wealth and fame and power. It's about how many shining eyes I have around me. So now I have one last thought, which is that it really makes a difference what we say, the words that come out of our mouth. I learned this from a woman who survived Auschwitz, one of the rare survivors. She went to Auschwitz when she was 15 years old, and her brother was 8, and the parents were lost. And she told me this. She said, we were in the train going to Auschwitz, and I looked down and I saw my brother's shoes were missing. And I said, why are you so stupid? Can't you keep your things together, for goodness sake? The way an elder sister might speak to a younger brother. Unfortunately, it was the last thing she ever said to him because she never saw him again. He did not survive. And so when she came out of Auschwitz, she made a vow. She told me this. She said, I walked out of Auschwitz into life, and I made a vow, and the vow was, I will never say anything that couldn't stand as the last thing I ever say. Now, can we do that? No, and we'll make ourselves wrong and others wrong. But it is a possibility to live into. Thank you.